I am going to focus a lot more on the deep learning side of things than the Hyak side of things. I did run some of the code that we did from the demo in Hyak, and we might get to that, but I will be polling a little bit to see what people are looking for, and then there will be limits to my Hyak knowledge, unfortunately. And certainly limits to my deep learning knowledge too, but those are a little further away. Awesome. So this is the plan for today. We're going to talk a little bit about understanding deep learning related concepts. There's many concepts related to the topic. Then we're going to talk about data and representations and learning tasks. And then we're going to talk about deep learning frameworks in the computing environment that we're doing this in, options, and then the hands-on activity. So actually training a couple of models using MNIST digit data, and then if you choose to, some flower data. Before I get there though, which is not on our list here, I want to get to just know who's in the room and kind of what experience people have and what people are interested in hearing about. So I'm going to ask for a raise of hands for a series of questions, just 3. So one is kind of conceptual understanding. Raise your hand if you feel like you have a solid grasp on how and why deep learning works. Okay. And then maybe the opposite of that, raise your hand if you're still learning or new to deep learning fundamentals. Okay. Yeah, sure. Raise your hand if you have a specific project in mind to which you're hoping to apply this session's learnings. Okay. And then raise your hand if you're just looking to gain general knowledge without a specific project at this time. Okay, so now final question is about data types. Raise your hand if you primarily work with image data. Okay, same for me. All of these are equal for me. Raise your hand if you primarily work with text data. Okay. Raise your hand if you primarily work with audio, tabular, or other data. Okay. Cool. So this, I didn't know quite where to level this. So we do have some kind of conceptual deep learning stuff that I will go through because there are some people who are interested in that, but I will try to kind of get through that or add more fill to it so that it's interesting and helpful for everyone. The thing that I randomly try to pick a Venn diagram from the internet every time I make these slides. This one's from computational neuroscience, but it's just fun to think about all of these different terms, how they are similar, how they overlap in the kind of broad space. So there are many. Don't take these Venn diagrams too seriously. I think there was just a year in 2012 where everyone was having fun making the most ridiculous Venn diagram with all these terms that you can. This is not the most ridiculous. Actually, I've seen much worse. But there are lots of different terms here. I'm going to just kind of quickly, to get through the concept stuff, go through 4. So we have artificial intelligence, machine learning, artificial neural networks, and deep learning. And kind of just throw in some basic information. I'm very, very happy to go on tangents, so if anyone has thoughts or questions, please do interrupt me. I think that's probably going to make this session better for the folks who came in with a lot of knowledge and more interesting. So on the artificial intelligence side, lots of definitions, no precise ones that you'll get from me, but think of something like mimicking human intelligence with machines. Yeah, that one is maybe the broadest, so you see it's on the outside of this weird kind of cornered Venn diagram here, but can cover lots of different ground. Doesn't have to be statistical. Could be a rule-based system or something like this with someone painfully writing all sorts of rules on how different verbs fit with different nouns and things like this. But then we can move in a little tighter to machine learning. So the ability to learn using past observations, those observations being data, without being explicitly programmed. Again, there's many, many different definitions, and this is supposed to be just kind of a high-level one here. Artificial neural networks, so now we're extracting and storing patterns using connected nodes, maybe inspired or backspired by neural networks in the brain. And then deep learning. So these are kind of more modern use of artificial neural networks, although we still use more simple forms as well. But there's many substructures and kind of high-level structure that we think about on top of just the basic idea of connected neurons. Okay, so now a closer look. So for machine learning, so a basic machine learning workflow often has something like this. We're preparing the data by collecting, processing, annotating it, doing some QA on it if you have that, which is great, some quality assurance. And then once we've collected enough, we're going to split that data into training data, validation data, and testing data. And the reason that we want to do this is because we want the model that we're going to create with the training data to generalize. And we want to test whether or not this generalizes by holding out some data to the side so that we can test it having not been used in training. Okay, then we train the model. And then we refine this model, often retraining it, often looking at the results on that on the validation set, maybe changing hyperparameters, doing all sorts of stuff there. So very basic workflow. This is probably familiar to all of you guys. So taking a data set, splitting it. And then the last thing I'll say on this bit is different machine learning paradigms. So most commonly, we're all in the paradigm of supervised machine learning, where we have raw data, but we also have some annotated or labeled data, and we're using that labeled data to do back propagation in the case of our deep learning or artificial neural networks to train our model. But there are many different types. So if you're not aware, semi-supervised machine learning. So here we may not have full annotated data. We may have some distribution of unlabeled data and maybe a little bit of annotated data, or some annotations that don't necessarily match the labels that we're trying to get, but do provide some signal. Then we have unsupervised machine learning. In this case, we're finding patterns in kind of the density or distribution of the data. And then we have reinforcement learning, which is very different, but a paradigm nonetheless. So this supervised learning is kind of what we're going to talk about in this. Pretty standard cycle, like I just said. We take the data, we label that data, and then we use that labeled data to train our model. We have an iteration cycle, and then we see those results. There's different ways to define a machine learning model. So we have like a discriminative approach where we're trying to define some line to separate different areas of the model. We also have a generative approach where we're defining some space, either with a function or things like this. This audience seems pretty advanced, but just to point out that this is very different from something that we might talk about for a generative adversarial neural network. In that we are just saying that we want to make a model that's defined by some function for the space, for these different classes in this case. We're not necessarily talking about generating new images or things, although those are often generative models as well. Okay, artificial neural networks. So getting closer to the deep learning yet again. An artificial neuron. Can someone tell me a little bit of what's going on here? So what are the X1 and X2? Yes, this is our inputs to our neuron. What are our W's and our B? Yes.
Bias.
So these are our weights and our bias. And so what we're doing here is we have some input data. So these might be pixels. So by the way, today we'll be very focused on images. I actually don't work as much on images, but it's much more fun to have slides with images on them than they are to see text or tables of data, which is what I see. So we have weights, we have some bias, which is another way to alter the value, the output of this function here, f. And then a key thing in this function, and then our goal is to output some y, whether or not that's a label or just the input to the next artificial neuron, depends on where we are in our network. It's important for that function to be nonlinear. Here are a couple of nonlinear functions, lots of reasons to use lots of them. Obviously, the ReLU on the right looks nice and simple. And sometimes the math, depending on how theoretical you're being, can be a little more interesting, but actually not harder, just different. But this is often what people are using, or fancier things than ReLUs. But just as far as getting started, ReLU is kind of the place to start. But the important thing, right, is that any of these functions that you use are nonlinear. Because if you had a linear function, then a chain of linear functions is just a linear function. And so now, we could have done this with kind of a slope. But so what we need is a chain of nonlinear functions so that we can start finding complex patterns across the many neurons that we have. Okay, so now we have our fully connected artificial neural network here. We have, in this case, 4 inputs. And then, so there's a weight coming in from all of those inputs. There's also biases. I'm not really showing that here. But then we can pass into an output. Cool. So if we think of this and we think of how we train a neural network, we have 2 kind of steps here. So one is a forward pass. So if you focus on the yellow this time, and we think about when we're actually doing inference, what we'll do is we'll take new inputs and we'll multiply them by these weights and by the biases that they have and continue to do those multiplications, likely on our GPU, until we get some outputs in the Ys. And then how do we fix those weights? Because we start out initializing those close to randomly, depending on what your initialization scheme is. But what we want to do is some back propagation to update those weights using the process kind of shown here in pink, where we're going to take all of these, or take the response that we get. So we have some output that we've made from this forward pass, or batch of forward passes all together. And we say, oh, well, that was terrible. That was a terrible result. Because I have the ground truth, I have labeled data, and I said, wow, what I came up with and what I was supposed to come up with, very, very different. I'm going to now start altering these weights. As long as this function is differentiable, I can start altering these weights to get me closer and closer to the values that I want to see. Okay. We'll skip this a little bit, but just thinking about the number of weights. So very quickly, these things start to grow. And you think, how do these models have billions of parameters? Well, these things can multiply out really quickly, and our neural networks don't look like this in deep learning very often, except for a little tiny, tiny part at the end. Okay, so deep learning. So one thing about machine learning, before deep learning really became a thing, is we had to do some work to come up with interesting features to pass in. And so that feature engineering, so this idea of, wow, do I take my data and do I square it, or do I change it to black and white? Do I, what do I do with this data to put it in the best form so that my model can find signal in it, is great. But even better when I don't have to do that feature engineering. And so that is what I would say is a big difference. So kind of this structure that you have, so much beyond fully connected networks, and then this kind of going beyond feature engineering. And this you see different in the workflow, right? So you're not having to do this feature engineering. You're simply using the sheer size of this model and the size of the data that you're training on this model to help to determine some of these features. And we'll talk a little bit more about what that looks like specifically for images. Okay, so speaking of images, here's an example, right? So we've moved beyond maybe what we see here with just the fully connected part. And now we see lots of different local structure. So we have a convolutional neural network, which is still used in, I think, applied cases, maybe not the new hotness anymore. But we can do things like have pools and have different kernels that we're looking across our image and so on and so forth. All of these different structures and tools.
Sorry, what are pools?
Yeah, so pooling is the idea of, let's say I have a window of a certain size and I want to downsample those pixels. So let's say I have a window that's 8 by 8 that I'm swiping across the image and taking some information. I may want to do things like downsample, reduce the information from that window, things like this, or gather other info. Some assumptions that we kind of rely on for convolutional neural networks related to images, right, are things like local connectivity. So this idea of if I'm looking at an image and I look at, let's say, a window of pixels, I might feel confident that pixels near each other can affect each other. They're highly correlated to one another. But pixels on the other side of the image may not be as correlated, or we may choose to kind of treat the pixels near each other as connected. So this is why we feel comfortable doing things like taking an image with many pixels and downsampling it, saying, let's take these 4 pixels in a little box here and just find the average value and call that a single pixel. Weight sharing. So weight sharing is all about, well, not quite all about, but if we look at a fully connected network, like we see on the right side of this here, we are having a weight for every neuron to every neuron, and those are independent of each other. Well, can I say that they're independent of each other? We want to treat them as such. Versus when I think about an image, what I might want to do is start finding similar patterns. So I might define some kernel that I will have pictures of later, but and use that same kernel across the entire image. And so in that way, we're sharing weights because we're using, because if you think of the kernels that we're learning during this process, we're sharing those weights across the image as opposed to kind of independently coming up with them on different parts of the image. And then pooling we just talked about. Okay. I assume folks have seen something like this before, just kind of using this kernel here, and in this case filtering, but doing lots of things with kernels. And filter, kernel, I kind of use different language here, but these, before we had deep learning, were manually engineered. There's research about the visual cortex and things like that, the sort of filters that people use or see that their visual cortex are using to distinguish different patterns, lines, outlines, that sort of thing, texture. And these are some examples that were learned from deep learning. So you see lots of things that are very similar, and you start to see kind of higher structure, starting to see textures, that sort of thing. So these are learned. So what's happening here is that over many images, we're coming back and we're back propagating, and we're altering the weights, and those weights, so if we're looking at this image here, this doesn't quite look the same, but you can think of these weights as defining these kernels here.
Question, is there a, going back to that, is there a task that was being conducted that produced this set of kernels.
Yes.
What was that task?
I don't remember this specific one. I imagine it was classification of images.
Okay, so some kind of classification produced this, but if I came in with a different set of images, I would get a completely different set of kernels.
You would. I would say that there is, I guess, lots of models you can very easily replace the tail end of the model with a different head or a different task. So change it from classification to, well, either classification with some different set of labels, or, regression, or segmentation, whatever you want. So you can exchange those things, and there are lots of commonalities between what you'll see at the beginning of your network. And this is largely from the very beginning, like the first layers. This might be the very first layer or second layer of the network. So I wouldn't say that changing it affects it that much. And this is why transfer learning works well, is that, the task that you're doing, certainly the data depends on it, but the task that you're doing and some similar characteristics of the data will find themselves looking very similar in kind of the early filters. That being said, of course, this is all stochastic, so you may not get this exact image ever again, but you're going to get things that look like this. Yeah. Now, granted, if your images look significantly different, and maybe going from drawings to something else, then now you're starting to see some differences. But honestly, some of these early filters are still going to look quite like this. Does that answer your question?
Yeah, I'm just really interested in, because I've heard of that last layer kind of substitution. So like an example would be, I build this from classifying dogs versus cats, and then I have a bunch of other images that are airplanes versus cars. And I can either say, okay, let's rebuild this from the very beginning and see what its kernels look like.
Yep.
Or I can say, let's keep these, but I'll do the the truth on a, as the supervised learning on my cars and airplanes.
Yes.
And see how this works.
Right.
Okay.
So yes, so I'll chop off the last layer or two, replace it with the new labels of car and airplane, and leave all of the weights in the model. So these are, the kind of visual representation of the weights. So leave all the weights the same, and you normally will have pretty good results from that. You're fine-tuning an existing model, and even though the images are different, and even though the task, I guess the task, if it's classification, are the same, but even if the kind of domain is different, these early layers are still very helpful in finding typical patterns.
That's really interesting.
Yeah. And then I didn't plan to go into transformers, but given the level of the group, if folks are interested, we can. But there are also transformers. This is not even close to part of what a diagram for transformers that will help you understand it would look like. But just to say that there is a lot of complexity, a lot of structure in transformers. These transformer blocks have quite a bit in them as well. But this all kind of fits into this larger story of deep learning, where we're now defining this model architecture with this structure, maybe using these implicit biases from what I expect for images or what I expect for text or that sort of thing. Okay, so that's it for the deep learning concept stuff. Do folks have questions before we quickly get through data representations and then move on to some of the software environment stuff? Okay. So data representations, I think you guys will all be familiar with this. So this is a grayscale image of an apple. These are completely made up pixels. I don't think that that's actually true, but excuse me. So what we see here is that, of course, it's made up of little pixels with different values. And that a color image is often made up of 3 channels, the red and green and blue, of kind of scalars for each of these that are combined. This is definitely made up. I think that's way too much blue and green for this very red apple. Okay, then on to text. And actually, we will see some of this with our classes as well in our image example here. But for text, we can represent it in many more ways. Another reason that I think images are a little more fun to do for presentations. But for text here, one way to do this is we have a fixed vocabulary. We might have a list of, often you see like 20,000, but it can also be like 200,000 words. And we say, this is our fixed vocabulary for our model. Here they all are numbered, plus punctuation, that sort of stuff. Another thing we can do is take then that long vocabulary and assign each vocabulary word a element in a vector. So it's a very long vector, 20,000 or 200,000 or more. And then each concept has a different element in that vector that it's assigned to, right? So even though apple and palm are referring to the same thing, I don't know French though, so I don't know if I'm saying it right at all. But even though they're referring to the same thing, right, we have no way of knowing this in a one-hot encoding. It's just a 1 in one spot and a 1 in a different spot. But, of course, then we can go further than this. We can use a model, actually, to find some embedding, find some encoding that relates these different concepts. And so now we have that apple and palm should look similar when we have this dense representation like this. So this dense representation versus a sparse representation, which doesn't tell us about the relationship between words. Okay, I don't think I have to convince anyone here, but data set sizes are getting larger and continue to do so. So these are research data set sizes, and I think this data goes to 2023. And these are just popular data sets that are released and used for, I think, specifically machine learning research. So data set size definitely depends on field, and there's certainly applications where people make do with much smaller data set sizes. But on trend, these things are really increasing, and there's a lot of reasons for this, right? Like these are really large, high parameter hungry models, and the more data we have, the better accuracy we seem to get out of these things, the less, not quite less overfitting, but the less we might overfit from a very small, not very diverse data set. Okay, so here's some tips, which hopefully actually I think are helpful for folks who actually are actively doing deep learning for reducing the data volume needed for your work. So one is something that we discuss, fine-tuning pre-trained models. So if you have a small amount of data for your application and you want to train a model on this, you will possibly find some success in finding a model that is similar enough and using that model architecture along with the weights of that model for this large data set and fine-tuning it on the data set that you have, right? So when we talk about foundational models or any of this sort of stuff, this is really built on this idea of fine-tuning a model with weights on a data set much larger, although much less specific than the smaller data set you have for your application. Transfer learning from other domains and tasks. So this is in some ways related. Often when you're fine-tuning, you're in a way transferring, but often when we talk about transfer learning, we're talking more about different tasks or different, like wholly different domains. And still surprisingly, can be very helpful to transfer from some domain that has a lot of data and use that model in your kind of smaller data paradigm. So you can inject manual feature engineering into deep learning models. There's different ways to do it. So certainly as we come up with specific architectures for your problems, this is really trying to account for some sort of implicit bias, as a word that we often use to describe, some characteristic of the data that we want to represent, we want to maybe use as a hack to get our model to work well. So if we can start to think about how we would manually feature engineer this and how we can get our model to take into account the fact that this data is symmetrical on this certain plane or something like this. Dimensionality reduction. So the more dimensions you have, the more data you need to fill up that space and to to have a high enough density in that space. So what you can do is reduce your dimensions and see if that works for you. This is something that people often forget, and it makes sense. You have data, and you don't want to get rid of the data. But if you have more rows than you have, or if you have more columns than you have rows, or relatively so, reducing the dimensionality, reducing the number of columns you have can be really helpful. Active learning. So if the problem is collecting data, it might be that you're collecting, data that isn't the ideal data for helping the model learn. So active learning is all about how do I choose the right data to give the model kind of the most signal about where I should move that decision boundary or something like this. So this kind of depends if you're in a paradigm where maybe you have a lot of data, but it costs to label it. Using models themselves to determine what to label can be really helpful there. And then finally, data augmentation. So if you have images or something like this, and one thing you really should consider is doing things like doing transformations on that data, on those images, and passing those through the model as well. It doesn't really help the data volume issue as much, but it is something we should consider and does increase your data volume. Okay, learning tasks. We'll go through these really quickly. So image classification, how can we assign a label to an image? We have a format kind of image and then some label. I work on evaluation metrics, but not everyone cares about evaluation metrics, so we'll not talk too much about those. Semantic segmentation. How can we segment regions in the image? How can we assign a label to either each pixel, or we might kind of draw some shape. So that's that. Object detection. How do we detect and localize individual objects in an image? So the data format to this can sometimes be similar. So some people use kind of a segmentation approach, this pixel level approach for object detection. But often when we're saying object detection, what we want is something like a box around individual objects. And we want to distinguish multiples, like even if they are partially overlapping or occluded, something like this, we're going to want that. Instance segmentation. So yeah, this is also quite similar, but slightly different here. So instance segmentation is kind of cross between the two. How do we want to detect individual objects and segment their boundaries? So this is different from semantic segmentation because I might say, I just care about the pixel that I can see. Maybe this is like this aerial view or something like this, versus I want to know how many objects there are and what their boundaries are. Okay, and as I said before, deep learning is often good at general, or actually maybe I didn't say this exactly, general feature extraction. You can change out this head, but this shape here in this particular example, this flattened vector space that we have here is a good thing to use as an embedding to represent the entire image that we just passed in. So now we have a list of, 400 numbers that hopefully well describes this input. Maybe we even test that using a decoder to see if we can come up with a function to take those 400 numbers and recreate that image or recreate that initial data. But that's for another thing. Okay, so now we're finally moving on to, again, a little bit of the software side of things. So deep learning frameworks and computing environment. So programming language, we'll stick with Python. I'm curious, actually, every time I do this, I normally get Python people, but does anyone use a programming language other than Python for their deep learning work right now? And what do you use? Any Julians? Any goers? Okay, and then high level, so there are many machine learning frameworks that I don't include here because this session's about deep learning specifically. There are still many deep learning frameworks that I didn't include here, but largely the two most popular are PyTorch and TensorFlow. We're going to use Keras, so I just threw the logo in there as well. Keras is a high-level API for TensorFlow. So you're using TensorFlow, but you have an API over it. How many of you have used PyTorch? Raise your hand. Okay. How many have used TensorFlow? Okay. Well, now I want to know decisively who likes PyTorch more? Raise your hand. Okay. Who likes TensorFlow more? No hands. Okay. My switch over to PyTorch was kind of early, but it was the moment I wanted to start editing my models and adding new ideas to those models. I found it much harder to do in TensorFlow. Well, that's unfortunate because today's session is going to be in TensorFlow, mostly because I didn't know what level this group was going to be at. And I find especially for domain scientists, a lot of the prior work that they're working with, like models and just materials that they have in their domain, tends to be in TensorFlow. And PyTorch isn't necessarily methodologist only, but it just seems to have less of that kind of domain backing. It also is newer, right? So this kind of makes sense. Okay, so we'll do this in Google Colab. These are cloud-hosted machines with access to GPUs. Just to kind of perfect our setup, I don't know, so not everyone here has an account on Hyak. I know we can use the, okay. This is partially why we're using Google Colab today. And then while I won't be using, well, we might have time. I think we will have time to get to it. I wasn't sure that we would be able to use it. But I just wanted to discuss a little bit about how I use Hyak in my kind of model training workflow. So I have my own GPU on my machine, maybe to justify more video games, maybe sometimes for deep learning. It depends on the day. But so I tend to use my personal machine or Google Colab to just kind of set up my model, run like an epoch or two. Some people say epoch, some people say epic. I'm going to say epic, but don't be confused by that. But just to run, like maybe 5 epochs or something like this to make sure that my model's actually working the way that I'd like. I'm normally doing this inside of a notebook environment, so it's all kind of messy and in a weird order. And then after that, I clean up my script, save it in a .py file, and then transfer that over to a much beefier machine and have that run there. So that is sort of the way that I like to go about this. I'm curious for folks who have used computing clusters, how many people kind of do it interactively on the compute there? How many people set up a batch process and let it run, sort of thing, without access to it in between? What are folks' setups? I guess that's what I'm curious about before we get into this. Yeah.
The BS code, like SSH plugin, is pretty excellent. So I use that with like a Jupyter notebook to like get nice working, and then obviously like a Slurm script to run.
Nice. Yeah, you're braver than I. I don't even try to set up my IDE to things, but I should. So how many people are not familiar with the concept of a container? Sorry, that was negative. So everyone knows what a container is? Docker. Okay, awesome. Cool. All right, well then let's move on to the hands-on activity. I do apologize. I think it's going to be maybe a little bit more deep learning focused. And so maybe we can try to do something live. Yeah. I didn't prepare the Hyak demo because I wasn't sure about time, but we kind of blew through this. So happy to do this quickly and then start moving it on to Hyak. Maybe just live. We'll just learn together live.
Yeah, and we can just kind of have a discussion about what problems you're running into maybe. And
yeah. So, okay, so if you go to this link, you can use your phone, but then you'd be stuck on your phone. So I suggest maybe going to bit.ly/Hyak DL-code. And at least we'll have a model here, very, very simple model, but a model to work with as we get this running. All right, so there is some, if you haven't used Google Colab, there are some settings that you can do for your runtime type. So requesting a GPU, I don't know that everyone has access or what work it took to get access to it. We can do this very slowly, like on our CPU, because we're just really setting this up. Sometimes it's nice to request a GPU just to make sure that things are running through your GPU, but we're using very high-level APIs, so that shouldn't be our worry here today. Okay. And the problem, I guess I should say, for the GPU is sometimes waiting for an instance of the GPU. Okay. But depends on the time of the day, time of the year, time of the week, sort of thing. Okay, I'm going to make this much larger. And we'll just run through this really quickly. So, Colab is Colab also, well, what am I trying to say? Colab is kind of Google cloud hosted machines. They do have a public container showing what's inside of the container that automatically launches when you open a Colab notebook. But suffice to say, it's a lot of stuff. So TensorFlow is already downloaded. Most computational tools that anyone in machine learning would be using is. So we're just going to go ahead and import, and we won't need to install. If you have specific domain-specific or specific packages and things like this, you may need to install those first. So you can just do a bang here, pip install, whatever you want it to install. Okay, but we can go ahead and import. So again, Keras is a high-level API made outside of it originally, but then brought into TensorFlow, so we can just import that from TensorFlow itself. We'll import map, excuse me, my throat, matplotlib, just because we want to visualize some things as we see what's going on here. So we're going to load some MNIST data here. We're going to scale those images from 0 to 1, just to be consistent with yourselves. I don't know, if you're a 0 to 255 person, I guess that's okay too. I'm a 0 to 1 person. So download some data here. We see we have 60,000 training samples and 10,000 testing samples. We're going to see this actually bite us a little bit. So this is MNIST. Well, we'll see it when it happens. But if you want to see some images here, I just have a little bit of code to see images. I'm sure you've all seen MNIST, maybe not in purple and green, but MNIST nonetheless. That's fine. So we have digits 0 through 9 and labels 0 through 9 for those digits. Okay. You can see now the labels are numerical and categorical. Not quite what we want for a model. We actually want to get to those one-hot encoded vectors. So we're going to go ahead and just use a utility to change it to a categorical vector here so that we can see something like this for our 5 instead of the number 5. Okay, so now onto our fully connected network. So we're just going to reshape into a one-dimensional vector, mostly to kind of keep things as simple as possible and matching what we see in lots of these images here of, let's see, did I put a copy down here? No, I didn't. so we see something similar to this, where we have all of our inputs in a row, and we're going to pass on from there. We can set our dimensions, so I'm just looking up the shape of not the first value, which is the number of images, but the size of those images. I just said 50 dimensions because why not? And then our output dimension matches our data, which is 10. Okay, so
Sorry, what was the side of the chip? Sorry, what was the dimension of the test images?
so the input is going to be 784. So this is the images. Yeah, sorry. So this is
So it looks like sort of 30 by 30.
yeah, 28 by 28, I believe.
Okay.
Yes, and right now we're going to shape them as a single one-dimensional vector, but we'll change that in a little bit.
Okay, and it doesn't really matter the way that that's mapped to that one-dimensional vector.
Correct, right. So for this model, we are just doing a fully connected network. We have no assumptions about locality or image-related things, so they could be in whatever order you wanted, and it doesn't matter, which, is not great because we know that location matters, but yeah. And then our output dimension is 1, of course, or sorry, 10, of course. Okay, so very, very simple network we have here. We're just going to have, so we have a model. We're going to add some layers. So we have a sequential model here. So we have a stack of layers. Then we're going to add a dense layer. So again, this is a connection between every node input and the layer that we're creating here. We're using a tanh here. For whatever reason, I decided to do that. And then we're going to add one more layer, and this layer is going to be our output dimension. And we're going to use a softmax, which is standard for classification here. Then all we have to do is compile this. We're going to use stochastic gradient descent with a learning rate that I honestly just made up and have not tested, but it's fine. It's MNIST. It's going to work anyway. And we'll split our validation 20%, and we'll just do 5 epochs. Batch size, I don't know how familiar people are with this, but this parameter basically is just telling us how many of these images we're going to do at a time in calculating our gradient descent. Okay, so we run this. This should take, honestly, like a minute or less. Actually, much less, something like half a minute.
Are you on a GPU or CPU?
This should be on a CPU.
Cool.
But we're only doing 5 epochs. We'd probably do something like 50. It's MNIST, so it's pretty simple. And so we see here we have our accuracy. So this is for our validation data or test data. And then this is our training accuracy. And this is our validation accuracy. I saw some code recently that's different. Does someone notice anything weird about maybe the relative values of these two accuracies? So we have our training accuracy, which is 0.85, and our test accuracy, which is 0.93. I know why this is this way. So typically we would expect, right, that our unseen data, our validation accuracy, would be lower than our training accuracy, because our training accuracy is saying, hey, I trained a model on this data. I have all the right answers. Now you've passed this data back in, and I've calculated the answers to this, and I still got a lower accuracy percentage than my validation accuracy. And why is that here?
I think that's because the batch size is, so you're updating your weights each batch per epoch, and then you're summing your loss for the training step over that. So you kind of can imagine you have like from has the model seen no data to 1 epoch worth of data, and the weights are being somewhat continuously updated. and then you're summing up the loss, whereas the validation gets run after the whole epoch. So it's only being run with all those. I'm not sure exactly if that's how Curious does this, but
Well, so that is true, and that is why, right, we see an increase of this quite quickly, right? Because once we've seen one epoch, now we're actually kind of more on equal footing, even if it's slightly beginning. But right, yes, at the very, very beginning, certainly the accuracy for the training data, we've seen no data at the beginning, and now that we've seen an epoch of it or epoch of it for the validation side. But that normally isn't an actual problem. Normally we still very much see validation accuracy lower than training accuracy. But the answer here is just more related to the variation that we have in each data set. So this data set was split, I think I put 10% in the, where do we go here? Okay, so like 60 to 10,000 training examples. And then I split this even further with our train data. Where is this? And I have a validation split of 20%. So what's happening here is the MNIST doesn't have a ton of variation. And what's happening here is that the small proportion of the validation data has so little variation relative to the training data set, which is much larger, that when you have smaller data sets like this, you can see this, especially smaller and simple data sets like this. So the way to test whether or not that theory is correct, which I actually haven't done before this, although I have in the past, I guess, is we could go and change this split. I guess I can't quite change it here, but what I could do is, let's see here, where are we? Our training samples. So let's do something like this. I could take my train and make it just the first 20,000 examples. And then we'll run everything else. Oh, what happened? Xtrain. Weird. Let's not do that though. Let's do. Oh, okay. It's just that the script, the ordering of my script is weird because I already ran this. This thinks this is this. So my pictures don't really matter though. So basically just to explain what happened here is I'm changing my X-train shape further down, but I'm assuming it's actually in two-dimensional shape for the pictures. So the pictures don't want to work because I've already made this one-dimensional with this code here. So that's fine, but let's just go ahead and run back down and run this again. And hopefully we see not what we're not seeing. Well, okay, so now we actually are seeing this. So now we're seeing the thing that you mentioned, which is the first epoch. There's a big information gap between the training accuracy and the testing accuracy, but we see very quickly that this catches up as opposed to last time. Although still lower, but okay. So there may be some other issues at hand. Okay.
I'm a little lost here. There's,
yeah.
I understand the separation between the training data and the test data.
Mm-hmm.
And then it seemed like there was a second subdivision of validation data.
Yes.
So how does one understand the validation data?
Yes. So these metrics that we see now are fully on the validation split that's been held. So actually, you're right in that maybe I should have changed this to 0.5 if I wanted to see this split more. This would actually be better for investigating this. But so this validation split is what's being used during the training process to measure accuracy. This test data that we haven't touched yet because we want to do this after we're done building the model to confirm whether or not it generalizes or not. So I think I may have led you astray by going to change the validation, or sorry, the test split up at the top. What I really should have done is change this validation split to experiment with my question here.
So the weights in the model are set entirely based on the validation
Correct.
subset.
Yes.
And then you go to the balance of the training data that's not validation to make sure that that's.
So actually, I have a slide on this that I kind of blew past. So let's go back. All right. So we have our full data set. And often what you do is you split your training and your test first. And your test data set is going to say completely siloed. This is for after we're done with our model. And then we take our training set and we split that into training and validation. So that's what we've done here. So we first split from train and test. Actually, we downloaded the data already split train and test, right? So that we all have the same test set. And then we are using Keras to split this again into training 80% and validation 20%. And so when we're training our model, we have labels for this training portion here, and we have labels for this because it was from the original training set, but we're using this to evaluate. So the val accuracy is from this validation set, and the accuracy, or the training accuracy, is from this training set, and we haven't touched this yet at all. Okay, cool. There's lots of other reasons that you might have your validation higher than your training data. Normally it's just problems, like issues, bugs, but when you have really small data sets like this tends to happen, or really non-diverse data sets. A thing worth noting for running this in a kind of computing environment is that we can store some sort of history here. So I haven't done anything fancy. We'll see this in a little bit. With my history, I just have a variable that model fits passing information to. So we have a callback here, but we're going to pass some more interesting callbacks so that we can really check what's happening in for a model, which is really important when we're running this on a cluster, because I may set it, let it run for a number of hours, and I'd like to know what happened in between and understand the object that's going to hold the secrets to what happened. Okay, so this code here, very simple. We don't have to really go through the code itself, but I'm just reshaping this into back into a 28 by 28 array. And now we have a convolutional neural network, a very, very simple one. So we take our input here. We have some 2D convolutions, and then we're going to define the number of filters. So those are those, when you see those like sheets of paper stacked up on the diagram, those are, the result of filters. So we want 32 of them in the first block, and then we're going to do 64 of them in the second block. And we're also going to have these pooling layers. So we talked about this. This is just downsampling the image. So I'm going from our kernel size, which is 3, to our pool size, which is 2. So we're reducing the size here, 2 by 2. And then finally, we're going to do kind of what we just did for the first model. We're going to flatten, but we can just use Keras to do that. And then we're going to have a dense layer for our 10 classes. Okay, so we can run that. See a little model summary of what's happening there and how many parameters this has produced for us. And we can run. So interesting things to note here, not too many. We'll just do 5 epochs. I increased the batch size for no other reason than speed. And I guess my validation split has changed because I'm just not paying attention to it. So we'll let this run. This runs closer to 5 minutes or so, at least on the CPU when I was at home. This might move a little faster here. Or not, or slower, who knows. Yeah, that was 16 seconds, much faster. But what are we seeing accuracy-wise? We really want to wait to the second epoch. All right. And so, yeah, this is the process. This is normally about, maybe 5-10 epochs is what I want to do on my own personal machine, or in collab if I'm, I don't know, trying to do work on my phone or something. I don't know why. Normally I'm using my machine. But just 5 or 10, making sure that this is running, making sure that this is, trying to converge, that we don't have any bugs. I don't know that this graph, ooh, interesting. I don't know what oh, right, I renamed this. Should not have done that. Apologies, you'll have to add CNN in front of history there. I don't know that this graph is very interesting to us at only 5 epochs. But much more interesting graph if we're running this for longer. So the last thing I want to say before we just get into kind of free-form Hyak questions and how we might do this on Hyak sort of stuff is some of the tips and tools and hyperparameters and approaches that I think are helpful when you're running this without your hands on it. So one is early stopping. This can be helpful. So often I wouldn't run something at 5 epochs. I probably wouldn't even run it at 50 epochs. I'd want to run maybe 200, 150 epochs. But often I will set up early stopping. So this is basically saying if I have, in number of epochs in a row where there is no progress, there's no improvement in the loss, just stop it. We're done, save that version. And so there's a patience parameter. This is pretty low. I would probably not set it for 5 normally if I'm running a much, an actual model that I care about. But for testing purposes, 5 is perfectly fine. I won't run this here because this will take a while. So this is something that we could run exactly this model with this setup on Hyak if we'd like. Other things to consider. Actually, I had a different data set of flowers. I think I didn't include this just for cleanliness, but dropout is very important if we are worried about overfitting, which we are in these very small data sets. Not very important. You can do other things, but dropout is another thing that we can add here. Maybe not so much a clustering thing.
Sorry, what is dropout?
Yeah, great question. So dropout is basically what we're doing is we're choosing some weights to just zero out the weight so that we're kind of just randomly dropping out a bunch of the weights, some percentages that you can define by layer. And this helps to kind of regularize the network. So yeah, just helpful to kind of guard against overfitting with many hazards. Not too many hazards, but some hazards.
Could that help with the lack of variability in the data set? Or in this case, it's going to overfit just because maybe overfitting is not as much of a problem because diversity is low.
Yeah, so normally dropout would be in a case, or normally we're worried about overfitting in the case where we've seen the opposite of this number. So what we saw here isn't indicative of overfitting because what we're seeing is actually we're doing better at generalizing than we were on the training data. Dropout is normally in a case where we're doing, like, it looks like our training accuracy is really high. We're like, oh, 99%, we're killing it. And then we look at our validation data and it's very low. This is telling us that we're probably learning some artifacts in the data itself, and we want to drop out kind of randomly some of this information so that we can hopefully be forced to have a smoother curve. So like regularization in general for statistics, you're kind of trying to force a smoother curve, and you can do that by getting rid of information randomly. And one thing I didn't add here, but I don't think it matters for this group, is things like data augmentation, so simple code to rotate images, that sort of stuff. But I think we're at a good point now that we have this code, I think we have 2 options. One is, let's try to get this to run on Hyak. The other is, let's talk about Hyak-specific issues that people are running into, and I will pass them along and maybe mime them on my machine so that we all have an example to look at. Okay, cool. So let's go with Hyak. Let's go with running this on Hyak. So one thing to do here is take our code, and I apologize, I don't have a second monitor, so you'll just see me flipping and flopping back and forth. We could, excuse me, just create a Python file. Because I don't want to do this in CoLab, I could, but why? Is this a reasonable thing to do in CoLab? Not really.
I tried it by doing like file and then download as .py
Oh,
at the bottom there.
I wouldn't trust that at all. Let's see what, yeah, we'll have to clean it up probably quite a bit, but that's fine. Oh, and then I probably should have opened it in something a little faster, but that's okay. We got there. Okay, cool. So yeah, we have our imports. Let's just go ahead and keep the MNIST stuff, delete. I mean, we can delete lots of the stuff, but we'll keep the printing stuff. Let's just delete the fully connected portion and stick with the convolutional. And then let's go ahead and we have a couple of copies of this. Let's get rid of the dropout for right now. It'd be better on a different data set. So now we have this. Do we need early stopping? Yeah, okay, so just to maybe make this a little bigger for everyone so we can follow along. So we have just text here, we have our imports still, we have our loading MNIST data section here. We have some print statements and stuff, it doesn't really matter. I should remove this 20,000 that we did for that experiment. Our plots and stuff we definitely don't need, so I'll delete these. Printing stuff you can keep. We will be able to see what's printed, but it doesn't really matter for us right now. Okay, so this data conversion stuff's fine to stay. I deleted all of the fully connected stuff, so now we have convolutional neural network section. We reshaped the data yet again, so probably could have deleted that, but we'll just leave it. And then we have our model. So sequential model here. We have a model summary function. Then we compile our model here. And then we fit our model here. And we have, how many epochs? Where did we put our epochs? 5. So let's definitely change this to something bigger, maybe like 50 epochs. And we could probably add in that early stopping. So maybe what we'll do is so let's go ahead and delete this CNN history here. And we can delete the plot. So we have our model compile as the last thing before early stopping. And then we'll call our early stopping, maybe with patience 5. I think that's okay. And I guess we're redefining epochs. We said we're doing 50, so that's fine. And we'll run this model. So history equals model fit here. There's quite a few things that we could add. So we could be saving this to a file. I think that probably makes sense. I'll have to check my notes to remember exactly how to save. I am not good at coming up with APIs on the fly here, or remembering APIs on the fly. I guess that's what Copilot is for. But let's see. Actually, let's just, where are we saving this at all? We're not saving this at all. So yeah, we should save this. let's just do a model save, the whole model at the end for right now. We'll call it MNIST CNN early stop 50. I don't know why I always make up a file type and call it .model and then just deal with that later, but you can name yours whatever you'd like. Okay, so now we have this. I would suggest when I do this, typically I would go and add to the callbacks a function to save between every epoch, or at least every epoch that has better weights. So that is typically what I do, but I have to go and look up how I do that. Okay, so but we have a model, we have the saved, let's go on from there. All right, so I'm gonna go to my terminal here. And I am going to look at my notes a little bit. Let's see. Oh, I didn't write down what the command is to, oh, there we go. Okay, so I'm gonna SSH into Hyak to clone here with my username. It's now a good time to pitch the STF accounts, maybe?
Yeah. So if you're a student and you want to start using Hyak, there's this group called the Research Computing Club. It's a group of students, and they've been able to get funding from the student technology fee, which is something that all of you students are paying into, whether you know it or not. And they've been able to get annual funds from this to add hardware to Hyak. And even this year, I'm the designated purchaser for them, and I'm about to add for a whole GPU node of L40S from NVIDIA. So almost every year they're adding $100,000 worth of hardware that you all could get a free account to use. And the STF accounts are some of the most stacked with hardware accounts that Hyak has. So in the follow-up email, I will put a link to the Research Computing Club website where you can apply for an account through them. And that's the best way to use Hyak.
Gotcha. Now I'm jealous.
I know, it's even more than what eScience has right now.
I'm sure, yeah. Okay, cool. So I'm logged in. This is what it looks like here. I like to clear my screen a little bit. I guess we're fine. The room is set up pretty well. So I'll just leave this at the bottom of the screen. Most of the time I clear to keep things at the top. So we have Hyak alloc here just to see what accounts and partitions I'm able to participate in. So I guess this is the GPU specific one.
Yep, so you have two GPUs, an A40 and a RTX 6K.
Awesome.
Which are the older kind. So.
Mm-hmm. Okay, cool. So then what I'll do here is, let's see, I guess I need to SSH, I need to copy over that code that we just saved. So I will remember where I saved it, or actually save it, which I don't think I did. I always get my logos confused. Yeah. Oh, no, I did save it somewhere. Where are you saved? All right. So yeah, I apologize. This was not intended to be a live demo, so we will be going with the flow a little bit here. First, by finding where this got saved. Okay, cool. It's right here. I hate the name of this, so I'm going to change it.
Yeah, that comma will cause problems.
It is upsetting me, yes. Oh, I must. I don't know how familiar folks are with these commands. I'm just going to do them and DL -model pi, something like this. Okay, cool. Then we will SCP it over into Hyak. Let's see if I want to do it this way. I guess I do. So we'll put our Hyak model and we'll send it to my username at Sorry, I already forgot.
clone.hyak.uw.edu.
Thank you. .uw.edu. And we'll just put it. See if I need a port here.
So what Bernice is demonstrating is to pass your files from your local computer to Hyak. She's using a new terminal that's connected to her local computer, not connected to Hyak, this terminal. So she's gone into her downloads folder where she downloaded the Python script, she changed the name, and now she's using server copy command, SCP, to send that script from her local computer to Hyak in this way. And she's given it the full path to her home directory where she's kind of pushing it into Hyak that way.
Yes. So I have 2 tabs going on, just as was explained. That was my personal computer. We can go back and look at Hyak here. And let's see where we are. Oh, we're in our home directory. So I see my Hyak DL dash model.
Yep.
Awesome. So I actually copied over from a tutorial that I saw on the Hyak website, a basics folder.
Yep.
So just so people can see where that came from. I don't think I edited it in a way that is significant, but if you go to the Hyak materials, I see many references to the great things in this folder. So let's do that. Maybe what we can do is really quickly talk through the different files that we have just from the tutorial. So we have our CIF files, we have our def files, we have some Python or script that we want to actually run, and then we have the Slurm files. So I mean, you're probably better explaining this. I can try to explain it though.
Oh, just that the SIF files, those are Singularity image files, and Singularity is the previous name of Aptainer, which is our container kind of runtime software service. And then the definition files, DEF, that is kind of like a container recipe file, so that's why it's called container build. And this directory is using a lot of, or it has a lot of files from many different tutorials that are available on our YouTube playlist, which I'll send to you as well in the follow-up email. Mm-hmm. And then we have .py scripts, which I'm sure you're familiar with, and then the .slurm scripts are bash scripts that are actually used to send jobs to our job scheduler Slurm. Yeah.
So here's an example of a .def file. So this is actually pulling a Docker image. This is the NVIDIA TensorFlow one, a certain version of it. And basically that's all that's happening in here. There's a folder being created, a couple of symbolic links to different folders, but that's all that's happening here. Like that's all that needs to happen is finding TensorFlow. The plus of any of these big deep learning libraries, the minus is that they have a ton of dependencies, but the plus is that once you find one that actually runs the software, which can be hard, most of your dependencies are going to be there. If we wanted to add things to that, we could as well. We could write more scripts to pip install things, to do all that sort of stuff after that in this def file here. And then I think I maybe have it in my history, but maybe not the best way to do a demo here, but Aptainer build. Yep. So we could Aptainer build into what we want this to be. So the name is unfortunate. I just copied it from something, but into a CIF file. With this def file that I'm just showing you right above this. I don't have to use that because I already have one right here, but we'll just keep going. And then now that I have this CIF file, I can, just go back through my history. Maybe that's the faster. I can Aptainer run it. Maybe I will do that one. Okay, and we see that the NVIDIA driver was not detected.
Yeah, it's because you're on the head node, which it doesn't have a GPU.
Ah, yeah. Okay. So maybe I misunderstood this. So what do I have to do to?
Just exit. And then, so if you wanted to start a job in your GPU, you would do salloc, and then -- partition,
Yeah.
and then it would be equals the GPU dash A, what was it, A100 or A40 in your?
Yeah, we can check.
A40. Yeah, in your Hyak alloc.
Yep.
Yeah,
So-
A40. Yeah, so then you would copy that. And you
Alright.
could just put dash dash GPUs equals 1, and that would just give you one GPU.
So sorry, eScience partition, the name of our GPU, or
Yep.
the name of our partition here.
Yep, and then
And
the
then GPUs equals 1.
Yep. Oh yeah, dash
Yeah.
dash GPUs.
Yeah, thank you. And do we?
You could do dash dash time equals 1 hour, just so it, I think that'll be enough time. Yeah, so it's 1:00:00. And then all the rest of the defaults are, it'll have one CPU as well, and it'll be on one node, which makes sense because it's, just one GPU.
Cool. All right, so let's run this.
So, and
When-
everyone who is following along with this hands-on demo, you'll have a different partition most likely, and you'll have to customize this command to use the access that you have. Yep.
All right, cool. So now we have our node.
So the only one change to make is that when you're doing your apptainer run command, you also want to add, this one, you want to add dash dash NV before the, if you scroll over to before 2.4.
Yep.
Yeah, and go dash dash NV. And this is required to carry over the NVIDIA settings to your container. So now your container will hopefully be able to see that NVIDIA driver because it's on a NVIDIA GPU.
Cool. So let's run this here. So now, we have no warnings about
Good.
our lack of GPU. Awesome. Okay, cool. So now we can get out of this here. And now, I actually hadn't run at all an interactive session, but I guess batch is the way that I would run a model most often. We can go ahead with that, or we can do interactive. You want to run a batch? I guess we can just slurm it. All right, I guess all right, so let's say we do want to run our script in batch now. I have a bunch of commands that I ran in the past. We could try to find which one was the request.
Or we could, I think you could wrap it into a script, or you could, since you're running on a job right here, you could launch the command, you could use apptainer execute, EXEC, and then give your dash dash NV dash dash bind gscratch, and then you do the container, and then Python, and then you could pass your script and try it that way.
Sure. Let's do it. So apptainer, sorry, I missed some of the.
EXEC.
Okay. Execute,
And
and then
then-
NV.
Yep.
And then what-
Bind
bind.
and slash gscratch.
Is it bind equals?
Nope, just space.
Space, yeah. Okay. G scratch.
And then I'll go over the parts of it. Okay.
And
then
then
the
Python?
container, or then your container name, so 24.07.
2.4.
Yep.
Then Python.
Yep. And I think your script is actually one directory above or closer to the root than you are. So
Oh, yeah, you're
you'd
right.
want to do dash dash, like that, and then do your.
And Hyak. All right, cool.
And you can try it. We'll see. Maybe there are more things that you have to do to your script, but maybe it'll just run straight up.
Oh,
Oh, yeah.
We need matplotlib as well. All right, let's get rid of the matplotlib in this. So let's just edit this. Do we have nano here?
Yep.
Because we don't need charts. We just did a poor job of deleting. Okay, we'll do that. Any more charts? Nope, looks good. All right. So now let's try it.
Okay. So what the command is, she's done apptainer, then execute, So that's just a kind of run command in the container. Oh, it's doing it. Is it still doing it? Oh, we had an error.
Let's see, yeah, more errors. Okay, this is my sloppy deletion, because this is the sort of thing that I would have found out.
So anyway, it was
Yeah.
apptainer. You can go ahead and edit that, but I was just gonna.
Yeah.
So apptainer and then execute, and then she says NVIDIA. So you're passing in your NVIDIA flag so that all your NVIDIA, drivers and everything are available. And then bind. She needs to bind the file system. One thing that's kind of hidden about Hyak is that you have this fully networked set of servers all connected together, but where your data is actually stored is a completely different server, and we call it gscratch. But the container doesn't necessarily know that. But to make all of your data on gscratch available to this container, which is fully isolated, right? You need to bind gscratch to it so that it makes those files that are outside of the container, like her Python script, accessible to the container then. And then she's calling the container, calling Python from within the container, and then passing in her Python script. So for you all that have a nicely built Python script that can just run out of the box, like you've done locally, all the testing, you know that it's ready to go, and then you've tested it with your container, so you know that the container has all the libraries and things that it needs to have, then this is kind of the best way to shove that command off a cliff. But if you have a longer running job, like she was saying, to wrap it into a batch script and use our job scheduler Slurm.
Yep. Awesome. Yeah, sorry, live demos mean that I don't really want to go and debug what
That's
import
okay.
I'm missing, but
You could try, so if you backspace, there's another,
yeah, there's that one in basics. the
that
TensorFlow.
tutorial, yeah.
Oh, we're in basics, I think.
So it's TF tutorial.
Yeah, so let's do that. TF tutorial.py.
So this is just a different script it's from Keras. It's their beginner basic learning TensorFlow script, or it's their tutorial turned into a script and used just to demonstrate this, this container usage.
Yeah. And more verbose than ours would have been anyway, which is good.
Yeah, it puts up the warnings about TensorFlow.
Oh yeah, that is a common sight.
But it'll look similar in that it's going to do the epochs now, similar to what you saw in the collab.
Yep. And 5.
But I do think that similarly, it would be fine enough to adapt Bernease's script to work in this way. It's just that, the container didn't have matplotlib, and it's just kind of we're going on the fly with this one.
Yep.
So
Yeah, this is this. Maybe talking a little bit about strategies for recovering this data. So I know if I did a Slurm script, I would define where this output is being saved. Mm-hmm. Is this output being saved anywhere now?
So this one didn't save any output.
Yeah.
But it would probably by default just be saved to the current directory. But you could specify where to save it and how to save it.
Yep. Yeah.
If you're trying to set up a deep learning, machine learning, any kind of protocol therein, my largest recommendation for you would be to use the NVIDIA container catalog online. So there are fully formed NVIDIA containers that are already very well set up to use CUDA and the NVIDIA GPUs that we have on Hyak. And I've found that folks have the best success in making a definition file like Bernease was showing earlier and installing the Python packages into a PyTorch container or into the TensorFlow container. And then you have that kind of contained, isolated Python environment with all of the dependencies that you need. And then you have your data on the outside of the container, and you can plug that right into your scripts for Slurm. That would be my recommendation. Another thing that I think this is kind of like the next level even of thinking about, okay, I want to I'm not just doing my research, but I want to make this model that I've trained into a product. Maybe kind of like what we were talking about, where you can transfer this learning. I don't know if I'm using that right. But you want to make it available so that someone else can follow your process for their system. I think a container is a great way to do that. I also think that if you can work with folks at eScience on like really preparing your Python script so it has all the arguments that someone, a user, can pass in, the dropouts, the weights, the number of layers, all of those parameters that go into fine-tuning your model, if they can be passed in as your arguments to your Python script, it's really, and even for yourself, it's really a great way that you can make use in HPC of a job scheduler so that you can in parallel be running all of these different parameters and combinations of parameters and finding, what is like the best, most recommended way for someone to run this model on their new data set.